right. So we are still in this process of finding derivatives, right? Again, that's not going to change here. We are still in this process of finding derivatives and figuring out every possibility that someone could throw at us to find a derivative. One of the things that we need to learn is this thing called the chain rule. Like, for example, if I was given this function, f of x is equal to the square root of x squared plus 1. F of x is equal to the square root of x squared plus 1. And I wanted to find the derivative of that. Could I use any of the rules that I already know? I mean, if I broke it up, I know how to find the rule. I know how to find the derivative of x squared plus 1. Okay. And I know how to find the derivative using a square root. But if it's combined like that, do I really know how to find the derivative? Okay. I don't really know what to do because it's kind of like two functions in one. Like I have I could rewrite it maybe that might help us. X squared plus 1 to the 1/2 power. Okay. So maybe I do the power rule where I bring it down 1/2 and then bring it down a whole unit. But then what happens with this x squared plus 1? Do I find the derivative of that? What do I do here? So that we will need the chain rule to differentiate things like this, where I almost have like a composition. Okay, and that's really what the chain rule is for. Whenever you have a composition of functions and you want to find the derivative of a composition. Okay. So here is the chain rule, and I would say this is the key piece to the chain rule here. Okay, this is the key piece to the chain rule. F prime of x, and they use capitals. I wish they used different letters, but whatever. They say the f prime of x, a derivative of a composite function. Whenever you have a function in another function, the derivative of a composite is f prime g of x times g prime x. F prime g of x times g prime x. Again, I love how they wrote this book because they said, okay, consider the function inside as like a function named u, right? How cheeky. I'm like, you're going to write F-U in the book. Yeah. It's like, this is going to high school, right? College. Right. I would never know. See, I did. Like, they definitely know what they're saying. They know. They get it. They have it. So if we let the inside function be another function, I like this notation because it's calling it g of x and f of x. So if I let the innermost function, let's call it g, be a separate function, and our purposes for the square root of x squared plus 1, the innermost function was x squared plus 1, right? The innermost function was x squared plus 1. And the outer function would just be the square root of it. So the square root of x. Okay. So what do we do here? We find f prime g of x. We find the derivative of the outer function with the inner function still in its place times the derivative of the inner function. Here's what I mean. Now, I would not try to learn this in Leibniz notation. I think that is really confusing. If you want to, this is how it looks. If you want to find dy dx, it's dy du over du times du dx. No thanks. Just give me this. I understand what this means. So let's actually do this. Let's figure out what the derivative is of this function that I introduced this with. Now, I think it is beneficial to rewrite it into this x squared plus 1 to the 1/2 power. Always take radicals and things in fractions and make them powers, like whether it's a fraction power or negative exponent. Okay, so what is this saying now? This is saying that this is f. And now this is going to be really, excuse me, that is g. The innermost function is g. Okay, red, please, thank you. And the outer function, this piece, is f. Okay? I know it's weird, I just kind of like drew over the square root, but the square root is the f piece of it. So what I'm going to do is I'm going to differentiate the outside of it. I'm kind of working my way inside. I'm differentiating the outside. Well, what is the outside? The outside piece is this 1/2 power, isn't it? So I'm going to do the derivative of that with the piece still inside of it. Right? That's kind of like instinctually what I think you guys would do if you didn't know how to do the chain rule. You would probably just do that and leave it there. But the chain rule says we not only need to take the derivative of the outermost function, but we also have to multiply it with the derivative of the inner function. What is g prime? What is the derivative of the piece underneath the radical? Just 2x. Okay, that's the chain rule. Derivative of the outer times the derivative of the inner. Now we just reduce it down. Okay, the 1/2 times the 2 will go away. So this is f prime of x, right? The 1/2 times the 2, that'll just become 1. So this is x times x squared plus 1 to the negative 1/2, of course. Hi, Mr. Colai. No problem. What's up? I do. Right now? Gotcha. Oh, no, we're taking notes, but he can just watch you. Okay, sounds good. Yeah. Hope you, Mr. Colai wants to see it. He said it should be real fast, so hopefully it's not too bad. You don't need to bring a shot. No. Okay, now, to reduce this a little bit more, I'm going to leave the x in the numerator, and in the denominator, I'm going to bring that down and turn it back into a square root. Okay. Hope we're good with doing those 2 steps at once. The negative exponent brought it down into the denominator, and the 1/2 power just put the square root back onto it. So that is f prime. That is equivalent to the slope of that function at any given moment. One of my algebra students asked me what calculus was. I told her. It's like, well, any equation, you find the slope of it. She's like, that's it? Evil laugh. All right. Again, this is just another representation of the same thing, another representation of the chain rule. In using the chain rule, we must work from outside in. Okay, working from outside in. We say if I've got d over dx of f of g of x with like a composite function, you're basically finding the outer function f prime of g of x. Like that's a tricky piece here. A lot of people try to change the inner function when you find f prime. The inner function stays exactly the same. You don't touch that thing. All you do is find the derivative of the outer applied when the inner is still in it. Times, and then that's when you take the derivative of the inner. Okay? So, let's try it again. Differentiate a and b here. So a is y is equal to sine x squared. And b, this is a, and b is y is equal to sine squared x. Now notice the difference here. Remember that we could rewrite this to say y is equal to sine x quantity squared, right? That's what that means, right? Look at what the difference is. The difference here is that in A, the squared goes on the x, and in B, the squared goes over the entire thing. Okay, no matter what, I've got to use the chain rule for both of these. Got to use the chain rule for both of these. Like, for example, this sine is my f, and my g is x squared. Now, in part B, my f is now the squared, and my g would then be the sine. Okay? I'm kind of like doing it two different, first and second. I'm changing the order of these things, two different orders. All right, so let's find y prime here. Y prime is going to be equal to, so it's f prime of g of x. What is the derivative of sine? Cosine, right? So it's cosine. Do I change x squared here? No, it's cosine of x squared times the derivative of g of x times 2x. So reducing it down, y prime is equal to 2x cosine of x squared. And that doesn't reduce. Let me just double check. No weird identities or anything. No, not in that one. Okay, let's look at part B now. Part B says, okay, now f is now the squared happening to it, right? Go outside in. Okay, I've got to do the derivative on the squared. So that means 2, and then knock it down to 1, right? That's really taking the derivative of the squared. If you have something squared, you bring it out front, and then you knock it down a unit. Don't change the inner function on that. I know I don't need that power of 1 there. I'm just putting there for emphasis to show you I just took the derivative of that. And then times the derivative of the inner. What's the derivative of sine? Cosine. And that, 2 sine x cosine x, that's a double angle formula. Y is equal to, y prime is equal to sine of 2x. Honestly, if you got here, though, that would be good, too. You good? Matt, you good?
Did you make that f because it's squaring the whole thing?
Yes. Like you take the outer function, you read outside in. So what's happening on the farthest outside? The square. So find the derivative of something squared. Sine squared.
Thank you.
Yep. Now this, I don't know. I could have gone without this. We good?
Yeah.
Okay. I could have gone without this slide. We don't really need this. This is just kind of like a summary of when I have a power rule with a chain rule. Okay? The power rule is just knocking it down 1. Like, read this in here. That's just knocking it down 1, bringing it down front and knocking the power down 1. I mean, that's just the chain rule. I don't know why we need this extra little piece in here. It's the exact same thing as just doing the chain rule. Okay, just reinforcing it here. Y is equal to x to the third minus 1 to the 100th power. So this, the 100th power is my f. This is my g. Read outside in. Work outside in. Okay, so how do you find the derivative of something to the 100th power? It would be 100 times something to the 99th, right? So y prime is going to be 100 times, well, what to the 99th? The exact same thing. Don't change it. That doesn't change. There. It doesn't change yet. Times, chain rule says, multiply it by the derivative of the inner. 3x squared. So all in total, y prime is 300 x squared x to the third minus 1 to the 99. Ooh, look at this. Look at what day I taught this on last year. November 2nd. November 4th. We're like right on. Yes.
Does it matter which one you make G and F?
Yes, definitely.
So G always is inside, no matter
Yes.
what? Okay.
Because it's always like F of G of X.
Didn't we just make the last one like F was the inside though, or no?
We should not have.
Okay. So F is always outside no matter what?
Correct.
Okay.
Okay, let's do another one. Ooh, look at that one. That looks fun. Again, whatever floats your boat, right? I do math. I like calculus. Other people like English and like writing. I don't like that. No, thank you.
I don't like that, but I don't think I like calculus either.
You know, high school is a time to figure out what you like and what you don't like, you know? That's why career tech programs are good, because, you know, you figure out what you like and what you don't like, and then you know what to do in the future. All right, so we have f of x is equal to 1 over the third root of all that junk, right? Okay, now I'm going to reduce it a little bit before I differentiate, okay? And that's going to happen a lot. I'm going to reduce before I differentiate. So please pay attention to the notation. This is still just f of x. I haven't done any derivatives yet. So this is like saying, how do I want to write this? X squared plus x plus 1. What would be the final power on that if I just wanted to bring it back up top and then take the third root off of it? Well, bringing it back up to the top, I would have to do a what power? A negative power, right? And what is this power here? 1/3, right? So this is like a negative 1/3 power, okay? Because the third root is a 1/3 power, and then if I bring it up to the top, it'll make it a negative 1/3 power. All right. So again, this is my f. This is my g. So the derivative of the outer, I take that negative 1/3, bring it down front, negative 1/3 times the original g. Knock the power down 1, so negative 1/3 goes to negative 4/3 times the derivative of the inner. Okay, the derivative of the inner is 2x plus 1. And now the rest of it, see, I left it like that on my key, but I think I could change that a little bit. I could manipulate that a little bit. Like this is all just going to be a negative. Let's put this chunk down in the denominator again. Right? There's also a 3 in the denominator. So this is x squared plus x plus 1 now to the positive 4/3 power. And now the 2x plus 1 stays on top. Okay, that's good. Maybe let's put the square root back, or not square root, but put the root in it. 2x plus 1 over 3 times the cube root of x squared plus x plus 1 to the 4th power. Because that's not making it more complicated, is it? But honestly, any of those would be fine. You get to a level in math and it's like, what is simplified anyway? Like what, yeah, like what's the end goal? The end goal is to find the slope at any given point, right? If you found it, if I gave you an x value, would you be able to find the slope with this function? Yeah. So it's like, okay, well then why do that? Because it looks fancy. Because makes us look smart. All right, let's take a look here. Now is when it starts to get real fun. Because we've got it. My definition of fun is this. Because now what we're going to do, I'm just going to say differentiate, and I'm not going to say differentiate by using the chain rule, because I just want you to find the derivative. Like for example here, if I want to find g prime of t, well, I know I'm using g, but f is out here, and this whole thing inside here is g, right? That entire fraction is g. Okay, so that means, I don't know why I'm going to switch to blue, but I am. 9 t minus 2 over 2t plus 1 raised to the 8th times, what do I have to do? What do I have to do to find the derivative of the inner? The quotient rule. So this is a quotient within a chain. And that's when it starts to get real fun, where you put multiple things, like you could have a product in a chain in a quotient. And then we're going to add trig into the mix too. Oh man, and then, whoo, let's go. Okay, so we've got f prime, let's think back to the quotient rule. F prime g minus g prime f all over g squared, right? Okay, f prime. What's the derivative of the numerator? 1. Okay, so it's 1 times g, 2t plus 1, minus g prime. What's the derivative of the denominator? 2 times the numerator divided by the denominator squared. Derivative of the top times the bottom minus the derivative of the bottom minus the top, or times the top, all over the bottom squared. And now from here, that's just reducing. And that's fun. So we've got 9. Let's reduce this up here, because this is 2t plus 1 minus 2t plus 4, right? Just distributing into negative 2. So this is 9t minus 2 over 2t plus 1 to the 8th times, so that's going to cancel a 5. That whole thing just becomes 5. Cool. That's fun. Over 2t plus 1 squared. Well, this is all just multiplication, right? So I can just put this all together. So this is 9. Let's call that 9 over 1. T minus 2 to the 8th. 2t plus 1 to the 8th times 5 over, oh, I wrote 2x. Oh, at some point I switched it to an x. I'm sorry. That's a t. Sorry about that. Times 2t plus 1 squared. Multiply all the way across on top. Gives me a 45 times t minus 2 to the 8th divided by 2t plus 1 to the 10th. Because I have 2t plus 1 to the 8th times 2t plus 1 to the 2nd. Well, same base. I can just add the exponents. Now let's multiply this all out to the 8th power. Just kidding. Just kidding. Just kidding. Just kidding. We got 10 minutes. No, just kidding. we really only have 1, 2, 3 examples left.
Sounds like a tomorrow problem.
So that's tomorrow.
Yep.
That'll be tomorrow.
Fun Friday.
On Friday, right there.
Anyway, I can definitely make it now. Ah, that would've been hard.
There's too much water in it. That's why.
Yeah, you're covered.
You know, you gotta put a little more umph in it.
Oh, it's so that was
And if there's more water in it, there's like more tendency
no,
to
it's just
tip.
oh, that's why that just stop you.
Oh, that's still being recorded. I'm gonna stop the recording real quick and then I'll put it back up there.